So let me give an introduction to VeriFast. So this is actually for a general audience, but I think it's sufficiently precise to be of use here. So it takes a C or a Java program input, annotated with function and method preconditions and postconditions, loop invariants, auxiliary logical definitions such as inductive data types, primitive recursive functions like fixed point functions in Coq, but more limited in what they can do, and proof hints like folding and unfolding predicates, separation logic predicates, and calling lemmas. It then thinks for a little while, usually less than a second, and then reports either 0 errors found or shows a failing symbolic execution path in a debugger like GUI. If VeriFast reports 0 errors found, this is supposed to mean, this is intended to mean the program has no buffer overflows or other undefined behavior, has no data races, threads, well, you know what a data race is, uses the APIs in compliance with their pre and post conditions that you specified yourself, and complies with the pre and post conditions that you specified for the program that you input. VeriFast is not supposed to ever report 0 errors found incorrectly. There can, of course, be bugs in VeriFast. There have been bugs, and there are definitely still bugs. The biggest known bug is, when I started working on VeriFast, I thought that C was just syntactic sugar on top of assembly language. So it was, I didn't know anything about things like pointer provenance, type-based alias analysis, so effective types, the presence of things that of indeterminate values, and that an initialized memory is different from initialized memory. So these are still there, except that I started fixing them this morning. So since this morning, you're no longer allowed to access an uninitialized local variable in VeriFast. So I also started working on making it not allowed to access in uninitialized heap memory, but I didn't finish it before this talk, unfortunately, but I think I might be able to finish it later today. So the pointer provenance is another thing I need to work on. So currently VeriFast considers a pointer to be an address. So the SMT solver type for pointers is int, and the casting a pointer to uint pointer type is just identity, so it doesn't do anything. So that's of course not sound. So I need to change that so that a pointer is a different type, and then you have functions from pointers to addresses, which are not necessarily bijective, of course, which are not going to be bijections. But I hope that this can be done without breaking the entire user experience. I think probably it should be possible to do that. So of course, the reason why I mentioned this is that many people, when they think of verification, they think of bug find. They only know bug finding tools like Coverity and Facebook's InferTool, and that's not, of course, what we are doing. So VeriFast is modular, like most of the tools I think here today. So it verifies each function or method separately. It executes the body symbolically using a separation logic-based representation of memory, starting from symbolic state that represents an arbitrary state that satisfies the precondition, and then checking that each final state satisfies the postcondition. And it uses the called functions or methods specifications instead of their bodies. So it's a function. It verifies one function at a time. So if it fails, then you get this kind of a GUI. Where you have the program, the place where the statement that failed to symbolically execute successfully, and if it was a call, then you also see the call site with the spec, and then you see the steps on the symbolic execution path, and for each step you see the assumptions, the heap chunks, and the mapping from local variables to symbolic values, which are SMT solver terms. And then you can step through that. So what did we do with VeriFast? One thing we did was verify memory safety and data race freedom of a C program that runs on a home gateway product of a European telecom operator. And we did find and fixed some data races in the process. Memory safety and card tearing safety of a Java card program running on the Belgian electronic identity cards. or actually, we don't know whether that's the code that actually runs on the cards. So the government says that this is the code, they provided this code to allow people to test their Java card apps against mock-ups of Java cards, but maybe it's actually the code, so we don't know. We also found a few bugs in that code. We verified memory safety and data rate freedom of the smallest Linux device driver that we could find, the USB boot protocol keyboard driver. We found a bug and it was fixed in the kernel. And we also verified memory safety, data rate freedom, and also functional correctness of some tricky fine-grained concurrent data structures, such as restricted double compare single swap, multiple compare and swap, a lock coupling set. The snapshot algorithm by Jayanti, which was used also by I forgot his name now, but by other people. The FSC, the tool, no, sorry, I'm completely blanking out here. So then also the Michael Scott queue and the Triber stack with hazard pointers. So we were recently, someone else used VeriFast for maybe the first time to verify some non-trivial piece of code. So Nathan Chung at AWS used VeriFast to verify memory safety, data rate freedom, and functional correctness of the concurrent queue data structure that is at the core of FreeRTOS. So the queue that's used for scheduling tasks in FreeRTOS, which uses interrupts, etc., for synchronization. And also people elsewhere used VeriFast as part of a tool chain. So this was completely unexpected by us. So they used it as one part in a multi-tool approach for formally verifying network infrastructure, such as network address translation tables. This was done in the Vigor project at EPFL. And what my own main use case for VeriFast is as a tool to help me validate ideas about new proof rules for various types of program constructs or patterns. So what we did with VeriFast was expressive fine-grained concurrency specification, safe and live exception handling, unloadable modules such as Linux kernel modules, absence of deadlocks in programs that use condition variables or that involve tricky patterns with channels that require obligation transfer. We worked on verifying termination of object-oriented programs with dynamically bound method calls, so modular verification of termination of such programs. Safety and liveness properties of I/O behavior, like I talked about at the Newton workshop earlier. And integrity and confidentiality of cryptographic protocol implementations, and also termination of programs that perform busy waiting. What we are currently doing, one thing we're doing is trying to add partial support for C++ and Rust. So we'll see how far we get with that. So we're putting Clang in front of VeriFast for C++ and the Rust compiler in front of it for Rust. And we're just going to try to encode the Ralph Jung's lifetime logic into VeriFast, perhaps slightly simplified, so that people can verify soundness of unsafe Rust code. So that unsafe Rust code preserves type system invariance. We also are working on generating machine checkable foundational proofs of correctness with respect to an accurate mechanized C semantics on a successful run of VeriFast. So first we were aiming for CompCert proofs, and so we have a very preliminary first version of that which just supports very simple while programs, so no heap access. And now we're targeting Robert Krebbers and Frederik Wiedijk's CH2O semantics. And then we prove also soundness of the CH2O with respect to CompCert so that we still get an end-to-end story. But we're at very early days in that yet. And then we have also been looking a little bit at combining VeriFast with something like a C-bounded model checker to try and see if we can get some synergy and get the best of both worlds. But that's even earlier days than the rest. All right, that was what I wanted to say. Thank you.
Okay, thank you. Ahead of time, thoughts, questions, interrupts, invisible raised hands? let me ask one, which I kind of want to ask everybody. So one thing that would be nice as we're kind of gathered all together and not writing single papers that have to expound the wonderfulness of each tool is to be more explicit about the, the things that you think are the limitations. So, what
right.
you just described some future work, which is in several dimensions, but what do you think are the problems with VeriFast?
Yeah, and to add to that, Peter, what's a discussion maybe of what would make, what would be a significant improvement to these tools, both in terms of the ability to, ease with which you can verify code, the scalability of the size of code you can verify, and the kinds of people who could run the tools.
Yeah. Or said more precisely, what should we collectively be aiming for 5 or 10 years down the road? But
right. So limitations of VeriFast. I think a major limitation currently is that we don't have this link to COC that VST has. So the kinds of full functional correctness verifications that Andrew and his team have done, they're currently not feasible at all in VeriFast, I think. So hopefully with this link to COC that we are building, we can encode, if we can encode the functional model in VeriFast, and then export that to COC, and then in COC we can do the link between, if we can prove the properties of the functional model. So that's one area of improvement that we're working on. An area, of course, that is, I think, maybe even more relevant to practice is more automation, reducing annotation overhead. That's, I think, the major thing, but it's very hard, of course, as we all know. It's something we always say we want to work on, but it's not necessarily the thing that is the lowest hanging fruit, academically speaking. So actually, I'm in contact with some people at AWS, and I hope to be able to work through AWS on real problems, and then hopefully that way I can get an understanding of how I can get VeriFast into a state that is more industrially usable.
Yeah. Craig says he would like the same question addressed to Andrew. So would I.
There's also a hand by
what are the limitations?
I'm sorry?
Sorry, I was speaking at the same time. There's also a hint by Fadim Saliba. So Andrew, I was teasing you. So like, what are the limitations of VST?
What are limitations? When your C program starts being clever in its use of data structures, the ratio of lines of proof script to lines of C grows fairly high, right? Easy, simple programs verify fairly automatically, but when I say fairly automatically, not as automatically as in VeriFast. VeriFast isn't fully automatic either. You have to fill in invariants and keep tweaking them until they're right, but it's more automatic than VST, even in VST's best case. In the worst case, or these C programs, when the C programmer is smarter than is good for them, then the verifier, the human interactive verifier, has a lot more work to do. And some of these programs, I am not sure how well they even verify in other verifiers, right? So the emphasis along in VST has been expressiveness, even at the cost of automation, more aggressively sometimes than in other verifiers.
What is a worst case? I don't ask this as it were to be nasty, but real curiosity. What is the worst case annotation overhead that one has?
I don't know, 100 to 1.
But
It's
really
not annotation overhead.
How many lemmas you write before you start verifying your actual function in order to prove entailments in your particular application domain as in a nice form.
Annotation overhead is the wrong phrase, because you do not annotate your C programs in VST. You have a C program over here, And over there you have a Coq proof script. So what you mean is, what's the ratio of the size of that Coq proof script in the worst case to the size of the C program?
Indeed.
And the best case, and we've seen lots of examples of the best case, is like 1-to-1. And the worst case is, I think, 100-to-1. But I'm not sure that, I mean, some of these programs, it's a miracle they can be verified at all.
Well, I have a question about this, because I assume that in your so-called worst case, most of it is, you're doing math, proving that the model actually satisfies.
Well, here's one thing that I was working on a VST verification for the last week that I thought would take 2 days and took 5 days. And why did it take 5 days instead of 2 days? This program, it uses concurrency. Concurrency itself is not the hard part. It's splitting up data structures to hand these fields, but not those fields, read only to that, through that lock, right? So splitting up arrays, splitting up the records into their different fields to hand parts of them through separation logic to somewhere else, and then rejoining them and prove that they join correctly, and prove that the read-only part that you kept really corresponds to the read-only part that you're getting back and they join. These things, I realize, it would be wonderful if there was a sort of automated theory of calculating this automatically. VST has a bunch of useful lemmas, but that was painful. So that's an example.
I think also in general, sort of all the user interface stuff is much slicker, of course, in something that connects to more expressive IDEs, and so like VeriFast, we don't have sort of these counter examples. And when tactics fail, it's difficult to figure out why they fail and what whether that's because of your invariant or because the tactic may be not covering all corner cases. And we haven't built that much sort of stuff on top of the existing Floyd framework. So it would be nice to have more in terms of proof synthesis or high abstraction levels for or reasoning support for the kind of splitting things that Andrew just mentioned.
So one thing about this thing about proof size, I mean, also it's a bit ill-defined because it really depends a lot on how much you have in your standard libraries. If you have, let's say, like a lot of theory about finite maps, and if you are verifying a data structure that's essentially a finite map, well, obviously that helps. And if you basically are counting that all to be part of your verification, yeah, then it becomes big.
Yeah. Vadim, you have your hand up.
Yes, I have a kind of more general question. If we're talking about a benchmark for functional verification, we might need to define what is functional verification with respect to this benchmark. For example, do we expect to get as a proof object, or we are fine if verification framework like VeriFast says 0 errors found? And I heard that they're going to work in extraction as a proof object as well, but do we require that, or are we fine with something else? So that what would be the definition, what we expect of the tool to provide in terms of the proof?
I think that this is another of the many dimensions in which these tools can legitimately differ. So one would like to record it rather than prescribe it. Speaking of recording, I am a bad person and I failed to say at the beginning, but you all know because it says in Zoom, this meeting is being recorded. If you don't want your words to be preserved forever on the internet, you should not speak your words. Any other? Ian, yes.
Yeah, so I have a question for Bart, and I'm interested. This is the thing you mentioned as prospective work of connecting VeriFast checks to formalized prover in the form of, if VeriFast says no error is found, one might get a proof in a tool, or it might emit a proof in a tool that the specification is satisfied. So what's your feeling about how closely you need to pin down the semantics of C, or is just your hope that even if what VeriFast thinks C is and what a particular proof tool or something like Composite thinks C is, may not be totally aligned. That's not necessary for the proof to work. If the proof works, then it's a proof. Or is this something where you need really close alignment between what VeriFast covers in C and what all the decisions it takes in edge cases and what the formal specification is?
So we're going to target CH2O, which is another semantics, just like ComCert in a way. And for some subset of programs that VeriFast accepts, this generated proof will actually be a valid proof, and for some other subset it will not be, and that will be something that we will push as we go incrementally, right? It will not be
okay, but you can get it, yeah, right. So it's absolutely valuable to have it working sometimes, because then you know it's worked.
Right.
I mean, this, as Peter indicated, yeah, all the different, exactly the correspondence between what portions of C you cover and in what way you cover it is going to vary, but that's survivable. This plan can still work.
Yeah, indeed.
Oh, neat.
Fred.
Just before I forget again, because I forget things all the time, because CH2O was mentioned, people have been talking about concurrency, whether that was interesting or not. But for me, input and output is very interesting. That's why CUT was one of the examples in this silly benchmark we made. Because CH2O, I don't think has really I/O semantics. I'm not sure, Robert should correct me. Anyway, I wanted to push. I would like to push input output for anyone for this benchmark ID.
Yeah, so I mean, we will be very happy if we can just prove memory safety of programs that don't perform I/O. But when we get to the point where we're happy with that and we want to look at I/O, then we will just add it to CH2O. I think it's not too much work, I think.
Enjoy printf, I say. Okay, maybe we should call on, who's next? Michael. Michael? Is fighting with Zoom in an inaudible way, I deduce.
While that's happening, I have a question, or maybe just a general observation. We've got kind of two ends of the spectrum here with BSD and VeriFast, and probably some of the other tools we're mentioning. One is the effort goes into putting the annotations in, and then you click a button and your proof is done. And in BSD, you're actively constructing the proof in Coq, but you're not really touching the C program. But also BSD supports an annotation mode as well. So I would assume that the kind of VST with annotations versus VST without, or VST, let's say standard, would have very different kind of, it's almost like a different tool that we're comparing in some sense. In some sense it's not, but in some sense it is. So kind of what would the expectations be of tools like that, which can support kind of either or mode? If VeriFast goes in the other direction of having, let's say, a fallback to Coq, then you've got this, you're muddying this distinction, which is not good or bad, but it makes comparing different tools and different approaches even more complicated.
Well, let me address the latter point first. Suppose VeriFast had a system for proving that the C program correctly implemented a functional model whose names were the same as, something defined in Coq, which is, I think, what Bart alluded to. I think these benchmark programs can have a clearly defined functional model, right? It's not up to the each application of the benchmark to make up a different functional model to prove the program correct with respect to. So The benchmark comes with the C program and the intended functional model, and even some strong suggestions about how the C program's data structures represent the things referred to in the functional model. And when I say strong suggestions, I mean, clearly documented, but of course the notation each tool will use to do that will be different. And so then it will be fairly easy to compare, let's say, VeriFast to VST, because they're proving that the same C program implements the same functional model. And if there's a proof somewhere else that that functional model has useful mathematical properties, and that proof is entirely in PROC, then VST and VeriFast alike can use it, and so can your tool. So I think specifying the functional model, if it's a benchmark that's for a two-layer verification of this kind, then just specify what the functional model is as part of the benchmark. That'll make comparisons much easier.
Can I ask, does that not sort of defeat a little bit of the point of doing the benchmarking? Because the interactive process of sort of using the tool to help you find the invariant is an important part of using these tools. And if that's really difficult, that's something that should be appearing in these comparisons.
How on a